Hi there, welcome to DNF Science. Today, we're going to be talking about the Born-Haber cycle. We're going to briefly go over exactly what it is and the concept behind it and actually how to picture it and draw it out. Afterwards, we're going to go over two example problems involving the Born-Haber cycle, in which case we're calculating the heat of formation, also known as the net energy change from the reactants to the products. Any and all documentation can be found for free as PDFs in the description, and with that, let's begin. So, the Born-Haber cycle, essentially what it is it's a method for analyzing steps of certain reactions. In this case, you're talking about reactions to form ionic solids. You can use it to calculate things like lattice energy and heat of formation. Heat of formation in this case is defined as the net energy change from your reactants to your products. The Born-Haber cycle is essentially an application of Hess's law. Hess's law states that the overall energy change, that is to say your heat of formation, can be determined by dividing a reaction down into various little different steps and then summing the energy changes in those steps all together. So let's go ahead and analyze how to navigate through this cycle. So here's the Born-Haber cycle. When we have a reaction, we want to start with our reactants, right? When we have a reactants, we first undergo through endothermic processes. That is to say, we're using energy to do things. And once we do all of these things, we have our intermediates. And our intermediates are ready to go through exothermic processes. That is to say, we're forming bonds, we're creating attractions, and these different processes are releasing energy as a result. So in these steps, you're going to have energy in negative kilojoules. After all these exothermic processes are done, you'll have your products, in which case one of them will be an ionic solid. So let's go ahead and go through these steps to figure out what they mean. Let's start with your reactants. When you have your reactants, they may or may not be in solid form, but if they are in solid form, you have to convert them to more readily reactive forms. The heat of sublimation, also known as the energy of atomization, is the input of energy that you're using to change from these solid reactants to more gaseous intermediates. When you have your gaseous intermediates, you can undergo further endothermic processes. Ionization energy is energy that you're using to turn atoms into ions by removing their electrons. Dissociation energy is also known as positive bond energy. It's energy that you're using to break apart bonds in a compound, usually to create individual intermediate atoms. From ionization energy, you create ions and also electrons. So when you have your intermediates ready, they're ready to undergo through exothermic processes. One exothermic process includes electron affinity. That's to say that it's the energy that's released when you're adding electrons to neutral atoms. Bond formation energy, also known as negative bond energy, is the energy that's released when you're forming bonds between atoms. It's similar to dissociation energy, but instead of breaking apart bonds, you're now forming them and also releasing energy. Lattice energy is usually the last step. It's the energy that's released when your gaseous ions are now bonding together to form an ionic solid. Lattice energy is also defined as the potential energy needed for the reverse process of turning an ionic solid into gaseous ions. The end product will have at least one ionic solid. The difference in energy between the reactants and the products is, of course, your heat of formation, and it can be positive or negative depending on your reaction. So now that we understand what the Born-Haber cycle is, let's go ahead and calculate the heat of formation in this example problem. Here we're asked to use the following data to estimate the heat of formation for barium bromide. We're given this reaction. Solid barium reacts with bromine gas to form barium bromide. We're also given this list of energies just for calculations. And here's just a little illustration of what's going on in this reaction. All right, let's get to it. So again, we're going to be starting with our reactants, right? We have solid barium and Br2. Now we notice that barium is a solid and we need that to be a gas, so what we're going to do is use the enthalpy of sublimation to convert that from the solid to a gas. And that's going to be 178 kilojoules per mole like we see in our chart. Now that both of our intermediates are gases, what we need to do is think about what we need to form BaBr2, which is an ionic solid. We need a barium ion and we need two bromine ions that are connected to the barium ion. So for the barium ion, what we need to do is just change that into an ion by using the ionization energy to remove its electrons. We use the first ionization energy to remove its first electron. We use the second ionization energy to remove its second electron. So now we have a barium ion and 2 electrons, but we still need to break apart the bonds for the bromines because they're connected to the barium ion and not to each other. So what we need is the bond energy, that is to say the positive bond energy, to break apart those bonds because it's still an endothermic process. So instead of Br2, we now have 2 Br atoms. So now here we see that all of our parts are assembled, and now it's time for moving on to exothermic processes. Now again, moving back to here, we remember that we need 2 bromine ions, not necessarily atoms. So what we need to do is utilize the electron affinity for Br. Now notice here that it's multiplied by 2, and the reason for that is the electron affinity for Br is in kilojoules per mole. And there are 2 moles of Br here. So what we're going to do is for each bromine atom that we have here, we're going to have this reaction. One bromine atom reacts with an electron to form the bromine ion. And so we have 2 moles, we have 2 bromine ions. And that's why this value is multiplied by 2. And remember, it's negative because here we're moving on to exothermic processes and we're forming bonds with each other. So here, again, we see that we have our 2 ions ready. We have our barium ion and we have our 2 bromine ions. So what's left is the lattice energy, and we're forming the ionic solid right now. And that is going to be negative, and here we are. All right, so now that we've gone through this entire process, let's actually figure out how to actually calculate the heat of formation. So remember, with Hess's law, the heat of formation is just simply all the tiny little steps added together. So let's go through them. The enthalpy of sublimation is positive because we're using that energy to convert from a solid barium to a gaseous barium. The ionization energy is positive because we're using the energy to break apart the electrons from the barium. The bond energy of Br2 is positive because we're using the energy to break apart the bond between the bromines. The electron affinity is negative because instead of using the energy to take away the electrons, we're now adding those electrons to the bromine. So that's why it's negative, because it's releasing energy as a result. Lattice energy is the energy that's going to be released when you combine these 2 ions, so that's also going to be negative. And so, with all these values added up together, we have negative 796 kilojoules per mole as our heat of formation. Alright, let's try a second example problem. Here, we're asked to draw the Born-Haber cycle and also calculate the net energy change for this reaction. Net energy change is, of course, just another way to say heat of formation. Here, the reaction is 2 lithiums reacting with 2 hydrochloric acids, creating 2 lithium chlorides and also hydrogen gas. Here is the list of energies that we're going to be using for the calculations. All right, let's begin. All right, let's start again with our reactants. We have 2 lithium atoms and we have 2 hydrochloric acids. Now, our lithium atoms are solid and want them to be gas. So again, we're going to use the heat of sublimation to convert them from a solid to a gas. Note here that we're multiplying it by 2 because we're using 2 moles of lithium. Now that we have our intermediates as gases, let's figure out what we need to do next. To get lithium chloride, we're going to need 2 lithium ions and also 2 chloride ions. Now, for our lithium ions, we're going to have to convert it by using the ionization energy to remove its electrons. So here, we're using the ionization energy to remove 2 moles of electrons from 2 moles of lithium. That's why we're multiplying 520 kilojoules per mole by 2. So here, we have our 2 moles of lithium ions, 2 moles of electrons, and also 2 moles of hydrochloric acid. Now note later, we're going to have to separate the hydrogen and the chloride so they can form lithium chloride and hydrogen gas respectively. So we're going to use the bond energy of HCl to separate them apart. Here I'm multiplying that by 2 because there are 2 moles of HCl. So here we have 2 lithium ions, we have 2 electrons, we have 2 hydrogen atoms, and we have 2 chloride atoms. Now we're ready to start with our exothermic processes. So what do we need here? Well, we're going to need 2 chloride ions, right? And to get chloride ions, we're going to have to use electron affinity. So for each chloride ion that we have, we're going to have this reaction. One chloride atom reacting with an electron creates a chloride ion. And because we have 2 moles of chlorides, we're going to multiply it by 2. So here we have 2 lithium ions, 2 hydrogen atoms, and we have 2 chloride ions. Now, we want to get hydrogen gas, right, H2. So we're going to have our 2 hydrogen atoms bond with each other, and that's using the bond energy of H2. And because we're forming a bond this time, it's going to be negative instead of positive, which is what you see here, 432 kilojoules per mole. Because when we form bonds, we release energy. So now we have our hydrogen gas and we have our 2 ions. Now we're just using the lattice energy to form lithium chloride, and because we have 2 moles of it, we're going to multiply this by 2 as well. So here we have final products. So now that we've drawn this process out, let's calculate the net energy change for this reaction. So for the net energy change, or the heat of formation, we're simply just adding up all these steps together. So for the heat of sublimation, it's the energy that we're using to convert from a solid to a gas. It's endothermic, therefore it's positive, and we're multiplying it by 2 moles because we have 2 moles of lithium. For the first ionization energy of lithium, it's the energy needed to remove 1 electron from lithium. It's endothermic, so it's positive, and we're multiplying it by 2 because we have 2 moles of lithium. For the bond energy of HCl, we're using that energy to break apart the bond between the hydrogen and the chlorine. It's endothermic, so it's positive, and we're multiplying it by 2 because we have 2 moles of HCl. For the electron affinity of chlorine, we're using this reaction. We're having chlorine reacting with an electron to form the chlorine ion. It's exothermic because we're releasing energy as a result of adding that electron, so it's going to be negative. We're multiplying it by 2 because we have 2 moles of chlorine reacting. For the bond energy of H2, it's us forming a bond, so it's going to be negative because it's releasing energy as a result, even though in the chart it's positive 432. For the lattice energy of lithium chloride, it's the energy that's released when we form this ionic solid, so it's going to be negative, and we're multiplying it by 2 because we're forming 2 moles from these 2 moles. So with all these steps added together, we have the net energy change as negative 562 kilojoules per mole. So that's the Born-Haber cycle for you. The thing that sometimes makes these reactions and problems a bit difficult is understanding what steps you need. And to do that, you have to know what components you want for your reaction. For example, if you needed the ions, you would go through things like ionization energy or electron affinity. If you need certain atoms or elements, you would break bonds, you would form bonds to get them. And when you're doing that, you have to figure out, is your step endothermic? Is it exothermic? Is your energy supposed to be positive or negative? Is it energy used or released? But once you understand the steps and mechanics and critical thinking behind your reaction, all these problems become relatively simple. I hope this video helps, and if you need these documents, again, they're in the description for free for download as PDFs. And with that, hope you have a good one. Oh, and thanks for watching.